Okay, welcome back students. Today we start the second lecture of our course on Introduction to Computer Vision. So today we will discuss the topics related to images and filtering. These are the basic topics that you should have studied in image processing course. So these are just like a little bit of a revision. So images, we can consider them as functions. So remember, all of you, they know. So here is an example of an image. So this is a black and white or grayscale image. So we can consider this image as set of values which we can plot on a 3D surface. So if you see this image over here, it has different values between black color, which is 0 0 0, which is, so over here we have only one color, so the value goes from 0 until 255. Okay, so if you plot these values, you will get a graph like this over here. So you see a graph over here. So the two axes over here, they represent the two sides of the picture. Okay, so x-axis and y-axis, they represent the two sides of the picture. So I think it starts over here. 0 0 is this point, and this is another one. So maybe you can say that one is x-axis and the other is y-axis, and then there is a third axis that represents the height or the value. Okay, so what happens over here, it has different values at different places depending on the image. Every image will have its own set of values. Okay, maybe I will write this one as x. Okay, and this one more closely represents y. So this is it, an image that I represent as a 3D graph, three-dimensional graph. This is another one, a little bit changed. So basically, image that you see over here, we will study it later on. This image over here is a little bit blur. So basically, what we discuss over here is that this image over here, it is same as you see the functions in mathematics. Let's say, for example, you have a function in mathematics, y equal to x square plus 3. All of you have studied linear algebra and a lot of different mathematics courses. So this is an equation over here, and it is something like function. Sometimes we write a y equal to like this also, f of x equal to x square plus 3. Yes, so in mathematics we already are familiar with the functions. So functions are a very common thing in mathematics. And what does this f of x mean? This f of x means that the value that you provide for the x value that you give, it will return you some output. Okay, so let's say you decide x equal to 1. So when x is 1, in that case the f of x or f of 1, which we also call as y or the output, it will be equal to 1 square plus 3 in this case. So it will be equal to 4. Okay, when x is 2, what will happen? It will become 2 square plus 3, which is 4 plus 3 is 7. Clear? So this happens over here, that there are two things in any function. There is an input, there is an output. Okay, so x value, we provide it as input, and the function will return me some output value, which we can represent as y, or we can represent it as the f of that value. Okay, so this is in mathematics. Same thing happens over here also. So basically there are three concepts that are quite similar. So one concept comes from mathematics. Okay. Another concept comes from programming. So in programming also, for example, you maybe you make a small function called square, and if you are using Python, you just write the name. If you are using C++ or Java, then you will write the type int x. Okay, so here I write the function def square, and inside what I am doing is just write return x multiplied by x. Okay, now whenever I call this function square with a value, so for example I call square 3, it will return me 3 multiplied by 3. The answer will be, let's say I save the answer in y variable, so the answer will be y equal to 9. So two types of functions you see over here. One is the mathematics functions, and the other is the functions that we have in the programming. Both of them, they are closely related. They have the same behavior. They take some input and they produce some output. Now the third thing that we see over here is that the images, they also behave like functions. So the summary of whole this slide over here is that these three things, they are almost equivalent, not 100%, but almost equivalent. Maths functions, programming functions, and images, these three are similar concepts. So how it works over here, in the case of images, how it can treat the image as a function? It is basically a function that takes two input values. So let's say I call my function f, it will take two values now. Now this time the y is not an input, y is not an output, it is an input. So when I will provide the value of my pixel position, so let's say x is 10 and y is 20, it will go over there. For 10 and 20, it will try to pick up the value and it will return me the value, which is maybe, for that place the value is maybe, normally there is one difference, that mathematical functions and the programming functions, they have some logic, some relation between the input and output. For example, here when the input is 3, output is double. Output is the double in power. Okay, so it is 9. But here in the case of images, there is no logic. It depends on the image. In this case, the image at this location, the image pixel has value 100. Maybe in another image, the value is 230. So there is no fixed logic. It is something you can say that as if the function values in the case of images, they are stored inside. And when I give some x and y position, it will return me value from that place. So it will return, for example, this value, and it will provide me this value. Clear? So this is the introduction, very important. You should know the difference. Three things, they are quite similar. Math functions, programming functions, and images, they are almost same thing. So here is another image. So each image is a different function. So this is a different function as compared to last one. Here is this image. This is in the graph form. And when you visualize it, here it is as a picture. So you see this picture is a little bit different. It's a blur picture. One more thing I want to mention over here, which we will study in this chapter. It is over here that you see if the image is more clear, you see the image is very sharp and clear. The image edges over here will be very pointy, sharp edges. So you see over here, for example, very sharp edges. Okay, whereas in this image everything has become less pointy, so the points are not so sharp, there are no spikes, and image over here is more smooth. Okay, more smooth. So when the image is smooth like this, it will have the it will be more blur image. So blurring is smooth image. Sharp image means that it has more details. Clear? So here is a small quiz which you can expect in the exam. I have put a lot of quizzes here in the slide just to give you an example what you can expect in your exams. So image, what we can think about it. So image can be thought of as a two-dimensional array of numbers ranging from some minimum to maximum value. This is true, this option. Why? Because the image that you have over here, most of you, all of you must have taken the course on image processing. Basically, the image is nothing but a matrix of numbers. So for example, there is an image like this. It is basically set of numbers in a matrix form. So this option is correct. Second option is a function I of x and y. So image also can be written like this. So you can give it any variable name over here. It is a two-dimensional function. You provide two input values x and y, and when you provide two input values, it will return you the image value at that location. So image can also be written as this option. And image is also something that is generated by the camera. So overall the correct answer is D, that all of them are true. Clear? So image you can write in mathematical form like this, I, x, y. It is generated by camera, and it is also something that is similar to the matrices. So we can think of an image as a function, f or I, you can give it any name. That is a mapping from R square to R. Now this thing is important for your exam also. Image is a mapping from R square to R, means that R square means that image is basically converting the two-dimensional function into a single dimension. Okay, so let's say over here you have a matrix. So what you see over here in this matrix is there are two dimensions, x and y. So you provide, for example, two values, row number 2 and column number 1, and it will return you the output for that place. So maybe that place has 15, so it will return you 15. So you are giving two input values. R means real number. So you are providing two real numbers, and the output that you get is a single real number. So basically your function, your image, it is mapping, or it is making a link between the two numbers, and it is converting them into a single real number. So I can ask you in the exam, for example, that image is a mapping from R cube to R square. That's wrong. R cube means that there will be three values. Normal images don't have three values. They have only two values, two position values, x, y. It is not a 3D image. And output is also a single number, not two numbers. So that's wrong. Similarly, if I write like this, image is a mapping from R cube to R, that's also wrong because this part is wrong, starting part. Clear? So f of xy, it gives us the intensity. Intensity means the value, the measurement, or value at that position xy. Clear? So remember, we can also sometimes practically define the image over a rectangle with some finite range. Sometimes we don't want to describe the complete image. In nature, the images sometimes are very big. We want to focus on a small part. It is very common in computer vision that you want to treat only one small part of the image. So in that case, we provide the minimum and maximum range of the image and the minimum and maximum range of the values. So for example, I explained that the image I consider is between 10 and 50, and 1050 is the starting point and the end point is maybe 100 and 200. Okay, and minimum and maximum range of the values, normally image values are between 0 and 255, as you know in many courses, media computation, image processing, you have seen this. But this value can change depending on the system. Sometimes the images are stored as values between 0 and 1. Sometimes they are stored between -1 and 1. Clear? So practically we define the image over some range with some finite set of values. Color images are nothing, just they are three images that we put them together. I don't know, I put an image somewhere for this. It's not saved here. So let me check. So color images are nothing, just they show you something like this. They are basically three matrices that are treated separately. So here I will draw it, color images. So if there is a color image, it is like this. Let's say this is one color and second color is like this, 4 values, and then there is third color B. So 4 values for everyone. So basically when we see the color image, basically what happens is that it is stored on the hard disk as 3 colors, red, green and blue. Remember, we discussed many times in other courses that color images are stored in computer using RGB encoding. RGB, red, green, blue colors encoding. So 3 colors are saved for 1 pixel. So when I want to make the color image, I will combine these 3 and I will display them together. So normally they are just stacked together. Stack means they are put together. Stacked means just like you put on top of each other. One and then the other is on top of that. Okay. So you see over here the R matrix, the G matrix and then the B matrix. They are put together. We call it a color image. But in this course, we will focus only on grayscale images. Okay. So the color images in this course, we don't treat them. We only treat the grayscale images because the theory is same. Whatever you do over here with the grayscale images, same thing can be done with the color images, but it will become more complex. So we will try to keep things simple and we will only be using grayscale images from now onwards. Clear? So here is an example. So let's say you have an image. If you want to see the part of the image, so let's say your image, its name is PD. So you store it in a variable PD in Python. So in this course we will be using Python. If you are not clear about Python at all, I will give you a lecture where you can make yourself comfortable with this. Okay. So here is the image. With this command over here, what does it mean? That you want to start from 40 until 60 on x-axis, and on the y-axis you want to start from 30 until 40. So what you want to do is you want to select a small patch or a small rectangle. Clear? This is how it works. So digital images normally, how they work, this is a little bit of theory. This is from your signal processing course, just to give a little bit of idea, just to revise. Typically the digital images that are stored on our computer, they can be converted from the analog images. So image or any signal which is not digital, it can be converted into digital by two steps: sampling, quantization. Sampling, if you remember from signal processing course, one more thing I will mention over here. Maybe it is a surprise for some of you, but in this course we will be closely following the concepts of signal processing. A lot of concepts of signal processing are used over here. So even to understand the concepts, we will give examples of signal processing and then we will use them over here. Okay. So if you remember in your signal processing course, let's say you have a pure sine wave, a signal. Okay. So this is your signal S. You want this signal, you want to convert this signal into digital signal. So this signal is analog. To convert it into digital form, what you will do is, the first step is you will do sampling. Sampling means that you sample or measure the value at fixed intervals. Maybe after every 1 millisecond, you try to measure the values. After every 1 millisecond, fixed time unit will not change. You use 1 millisecond, you always use 1 millisecond. You use 10 millisecond, after every 10 millisecond you will take a sample. Okay. So here it is, you see, you will sample it, and then in the third step, or in the second step you can say, after the sampling, what you will do is that each sample that you take, you will convert it into a digital value. You will represent it with the binary value. So let's say first sample you represent it as 3. So in binary 3 is equal to 0, 1, 1. Second value is 5. In binary, maybe you use 4 digits, 4 bits. So 5 will be 0, 1, 0, 1. Then the next value is 7, maybe, just an example, and so on. You will keep on doing this for all the values. You will convert them from analog. First you sample them and then you round them off to the nearest digit. So this is how it works. The images are converted into digital form when we want to scan the images, for example. Okay. So when you use a scanner, it is basically converting the real life image into a digital image. Whereas in the case of digital camera, the images are directly stored as digital images. So remember, the word digital image means that image is stored as pixels on your computer disk. So digital images, they are basically those images that are represented as a matrix of integer values. So here is the example. So this over here is a digital image. Practically it's stored on your computer like this, a matrix. Okay. So when we want to convert, this will happen a lot in our course, that when we want to discuss some concept in computer vision, we will give an example and we will discuss it on signals and systems course. So we will take, for example, one signal and we will show that what we are doing. So here you see the sampling step you are seeing over here. Analog signal converted into samples. So MATLAB, we will not use MATLAB in this course, we only use Python. So ignore MATLAB. Instead of MATLAB, One interesting thing is that the computer vision library we will be using, CV2, it is using the same names as MATLAB. MATLAB and CV2, they use the same names. So the same function we will study over here also. So in the lab part, we will see this in detail. So we will cover this thing over there. We can easily, so this is the Python one. That was MATLAB. You ignore the MATLAB, but the Python is what we will do over here. One more important thing, remember, in this course, because this is the course name is Applied Computer Vision, so lab part is more important. So it is so important that it is part of your exams, midterm and final both. Everything that you study in the lab, it is as important as your lectures. It can come in the exams. So you can be given asked to write code, small codes, 2-3 lines. You can be asked in the exam. Clear? So here are some of the instructions. What they are doing is they will load an image like this. The instructions we will study in the lab part in detail. So no need to go into details. For now, what does it mean? That these instructions, they load this image which is for these vegetables. One more thing that occurs with any type of images. So remember, images, they are similar to signals. So if you remember in your signal processing courses over there, it is discussed that, for example, you have a signal. Let's say it's some audio signal, analog audio signal. You want to transmit it on the channel. So for example, on the radio. Okay. These signals are normally disturbed by some sort of thing called as noise. Okay. So noise is a problem that disturbs everything. So the result is your signal plus there is some noise. So how to deal with this noise? That's a big problem. That's the problem. Same concept is over here. You have an image, you store it, you save it, you are using it somewhere, sometime, some noise comes in this image. So we represent an image over here. This is your original image. And a noise is added to this image. Noise, what is noise? Noise is basically unwanted information, unwanted signal. Maybe it is some other signal. In the case of signals, for example, this is signal 1. Maybe some other channel's signal, S2, can be a noise over here. It will disturb my signal. So that S2 is also some information for someone else, but for me it's useless. So it happens like this, that it becomes noise. Same thing here. I have original signal and it can get some noise. Important thing about noise is I don't know what it is exactly. It's random. So these original and the noise, they together form a modified image. So I prime over here that you see, it's a modified image. So noise is just another function that is combined with the original function to get us a new function. So here are some of the examples. These examples we will cover in full detail in our lab part. Okay. The first type of noise we cover over here is called the salt and pepper noise. So salt, you all know what it is. The salt has normally the white grains. Okay. Whereas the pepper is the black one, it's filfil. So it is the one that has those black grains. So we call this noise salt and pepper because it is producing white and black dots on the image. Lots of white and black dots. And the problem is that they occur randomly. You cannot predict where they will occur. If you can predict, then you can easily remove. So they occur randomly anywhere. You don't know that any part of the image, is it real or is it because of the noise. So these are the random occurrences of black pixels and white pixels that occur on the whole image. So this is the original image and this one is with the noise. So this is the first type. Another noise is called the impulse noise. Why we give it the name impulse, that will come in the future chapter when we study impulse. But impulse noise is the one where we have only white dots. So random occurrence of white pixels only. So if it is white and black mixed, then it is salt and pepper. But if it is only white, then we call it impulse noise. So these are basically, in the previous case, in the salt and pepper, the black pixels, their value is 0, and these white pixels, their value is 255. So these are the extreme values that are inside the image. Here in impulse noise, we only have these higher values, 255 everywhere. Whereas the third one noise is more difficult. It is called Gaussian noise. Gaussian noise is a noise that is mixed everywhere, and it is a value that is based on Gaussian normal distribution. What does it mean? It means that the value over here, it is same as the surrounding pixels. So let's say your pixel over here, its value is 120. The noisy pixel that is next to it, it will have a value a little bit high or a little bit low. So maybe one has got 125 and the other has 112. So this extra value that is coming over here, maybe the difference of 5 plus 5 or a difference of minus 8, this is basically the normal distribution. The value that changes according to some pattern. So normal distribution is the concept that comes from probability and statistics. I don't know if you remember or not, or if you have studied it. This must be in your course of probability. So I gave an example. Let's say you have a class. So normally in the class I give this example. Your class starts at 11 o'clock. Okay. And your professor wants that students should settle. And then he tries to give them some extra time and he comes a little bit late. So professor comes normally at 11:05. Clear? So this is the normal time. But what do you think? This gap, that is the 5 minutes gap, this is decided by the professor, but it does not mean that the professor will come exactly at 11:05. Maybe you take the watch and you try to note down the timings of the professor. You will note down, maybe some days professor comes at 3, sometimes he comes at 4, 11:04, sometimes at 5, and sometimes maybe at 6, and sometimes at 7. And very rarely that professor is coming too early, 11 o'clock 01. Or very rarely, maybe because of some problem or some meeting or something, a professor comes at 11:10. So what happens is that if you make a graph of the professor coming to the class, you will note down that mostly the professor will come in this area. So it will be a graph like this. So most of the time professor will be coming at some place, and this value that comes in the middle, it is called the mean value. That's what you study in your course of probability statistics, mean of the distribution. Mean means the average, the center. Clear? So professor can come early or late, but on the average he will be in the middle. So this shape over there, it is called normally as the normal distribution shape, or it's called the bell shape. Its shape is more like the bell. So we also call it normal distribution or Gaussian distribution, and same behavior is over here. That's represented over here in this image. So whatever is the pixel value, that value changes a little bit up or down around the original value. So this type of noise is called Gaussian noise. So Gaussian, the name Gaussian comes from the scientist who proposed this distribution first time. His name was Gauss. Okay. So, and this type of noise is more difficult to remove. So because of this noise, there are no white or black dots, but the image becomes a little bit rough, or not so clean, or not so smooth. Clear? So we will see in the lab. Here you see the example. So this is the image which has no noise. What you see over here is that they, on the image, they select one line of pixels, and the line that you select is shown over here. So I select all the pixels on this horizontal line, and these the values on this line, they are shown over here. So this line that you see, it is shown here. So this is the original pixel. You see over here these values going up or down. Now I show you the noisy version. So here you have noise and the Gaussian noise. So you see, instead of the previous two approaches, impulse noise and salt and pepper noise, here the image has the same pattern. So the pattern is same, but noise means that around that pattern the image is fluctuating, changing. So if the image value is around 10, the noisy image value is also around 10. So it can be 12, or it can be 15, or it can be 5 or 7, but it is same. Here the image value is 100. The noisy image has same pattern. Over here it will have maybe between 120 and 80. Clear? So this is called the Gaussian noise. The noise that fluctuates, that changes around its center or mean value. Okay. So sigmas, there are a lot of examples of sigmas here. Ignore all those examples. Sigma will not study in our course. So remove this, also this one. So here is the example. How to show images in Python. We will have a separate lab on all this thing. So we will discuss over there. So I am sure will come over here, there. So here is a quiz, some questions you can expect in the exam. Make sure you understand these questions. You will not get same questions, but questions will be tricky like these ones. So when adding noise, so the question is, when adding noise to the images as arithmetic operators, we have to worry about. So what is the important thing we should worry about? So the speed of the addition operation, the magnitude of the noise compared to the range of the image, whether we add noise to the image or image to the noise, or none of the above. Now this is a tricky question, I will accept. Okay, let's discuss them one by one. You can pause the video and you can think of the answer yourself, and then you can compare. So here is the first answer, that let's say you have an image. What's the question first? Question is that you have an image and you want to test this image, for example, related to some noise. And in the lab, you try to put some noise yourself. So it's a common thing that you try to make a bad image so that you can test some things, some functions, some algorithms we will study in the next chapter. So when you add a noise to the image, so when adding a noise to the image, what is important thing that you should consider? First one is speed of the addition operation. When you are adding, how much time it will take? So I don't think so. Time is not important because the computers now have become a lot of much faster. It is important, but still not so much important. What can be the second option? The magnitude of the noise. How much bigger is the noise? Okay, now that is important because let's say your image normally has values between 0 and 50, all the values, and the noise is bigger. For example, noise has the values between 0 and 200. In that case, noise will almost destroy your original image. Nothing will be left in the original image. So this option is important. The third one, the order of the addition. You add the noise to the image or image to the noise. So here you add noise to the image, this one. Whereas noise is already there and you add the image, it does not make any difference. In the next chapter you will see these operations, they are commutative. Noise plus image is same as image plus noise. It makes no difference. So option B is correct, all other options are wrong. Clear? Next thing that comes is called the filtering. So before we go for filtering, MATLAB, leave this. In Python, remember, we will be studying Python in this course. In Python, all the numberings or indexes, they start from 0. So for example, if you have an image, so image is represented as a matrix. So matrix position starts from 0. Okay. So the top left corner of the image, it is 0, 0. So finally, one more confusion to remind you is that in computer science normally indexing typically starts with 0. In many other programming languages, I think in C++ also, the indexing starts with 0, 0, 0. So in Python, the indexing will start from 0, and that's why the top left corner or the origin of the image is 0, 0. So here is the Gaussian noise, another example. So this is original image, whereas in the case of noisy image, you see there is a fluctuation in the original value. So the image, you can represent the ideal image like this, and then you can represent the noise something like this. Noise, remember, is just like any ordinary signal. The only problem is that this signal is not meaningful for us. But other than that, it's a pure image also. Now the important question that comes is how to remove this image, this noise from the image. So how to remove these noises, that's a problem. So there can be a lot of different tricks. One common trick that comes in mind is that, let's say you have a pixel over here 20, another pixel value is 15, 21, and then 30, and this is a noisy pixel over here, its value is too high, 50. So this one is noisy. So how to do is how to remove this noise. One thing can be that you take the average of all these pixels that are in the surroundings, and then you take the average. For example, all those values you add along with this one. So there will be 9 values divided by 9. So there will be 9 values you will add. So you will have 20 plus 15 plus a lot of values, and add them up and divide it by 9. This is the averaging. This is one example we can do. How it works, here it is. So let's say, so remember I gave you just one example before. I said that the concepts that we discuss about images, we will first discuss the theory on the signals, and then we will come to the images. So here is a signal, and this signal has got some noise. So it's a Gaussian noise. So it is a little bit different from the normal values. It can be a little higher or little lower. In any case, if it's higher, for example, maybe this is lower one is also noise. I don't know. So in any case, these are the different values as compared to the others. So when we take an average, what does average means? For example, if this is my noisy pixel or noisy value in the case of signal, I will take an average over the surroundings. Maybe I select 2 values on the left side, 2 on the right side, and 1 in the middle. 5 values I take an average and I divide it by 5. So I take the values and I divide it by 5. It will give me the pixel value like this. Now it is corrected. Clear? So this is the first attempt. What we want to do, replace each pixel with an average of all the values in its neighborhood. So this approach we call it moving average. Okay. This approach seems reasonable. It's okay. But the important thing is that for this approach to work, there are 2 assumptions that we make. Now these assumptions are important for your exam also. What are the assumptions? One assumption, let's see, 2 key assumptions. A little thought and you will realize that there are 2 key assumptions for this thing to work. So the assumptions are that the true value of the pixels are similar to the value of the pixels nearby. The pixels that have the values, they will have similar values. For example, here it is 20, here it is 15, here it is 21. So there should not be any change in pixels suddenly. So sudden change in pixel values, that's dangerous. For example, I want to show some person standing in front of the wall. So the wall is maybe a black color and the person is wearing a white shirt. So that value black, maybe it's near to 20, near to 0, whereas the shirt will be very high value, 200. Okay, now this is the trouble, because how you will make a difference between the value and the noise? That's the trouble. So true value of the pixels are similar to the value of the pixels nearby. All the surrounding pixels, they have same values with little bit of variation, not too big variation. And second thing is that noise that is added to each pixel, it is done independently. Noise is added separately to each pixel. So let's say you have same values 20, 15, 10, 30, 25 and 20. Now all these values are almost in the same range and the noise is added to this pixel. So in the 25 we add a noise of 30, so it becomes 55. Okay. So noise is added to each pixel separately. So this 55 comes over here. This has nothing to do with another pixel. So there is another pixel with a value of 20 itself. Noise will add up over here separately. It has no addition effect. The past value does not make a difference here. So maybe over there 30 was added, maybe here we add 25. So the result is 45. So two assumptions are important. One, the whole neighborhood or the pixels that are nearby, they have similar values. Not exact same, but should be in the same range. Not too big difference. Second thing is, the noise that you add, they are added independently to each pixel. Wherever we want to add, it's added to that pixel without any effect from the past. So here is another quiz that you can expect for your exam. If noise is just a function that is added to an image, so remember in the previous example we saw there is an image, you add a noise, okay? We could remove, so if it's just a function that we have added, we can remove the noise by subtracting the noise again, isn't it? That means that the operation is reversible. So this is an image I plus noise, it gives us I prime. What they want to say is that we can just subtract the noise from I prime. Then we will get our original image, I. So what do you say? True or no? So is it true? Is it true? But we don't know the noise function. So it is not true 100%. If we can subtract the noise like this very easily, then the whole course of image processing is finished. No problem. We don't need image processing course. So it's not true 100%. What's the problem? The problem is that we are allowed to subtract anything from the image, but we don't know the noise function. Remember, I told you noise is random. So you don't know for each image how the noise has disturbed this image. So we can't actually do the subtraction because we don't know what is this noise exactly. Okay. And last option false. Additive noise destroys information in the image. That's not correct. We can recover it, but we don't know what is the exact noise that was added to this particular image. Clear? So I think this is enough for now. The weighted average, moving average is an incremental topic we will cover in the next class. So if you have any questions, please ask in the group.